time for us to begin. So last time we talked about the course policies, and we said, well, okay, here's what differential equations are about. And our big goal, of course, is to solve, which means I have some equation which involves a derivative. Maybe I have like a y prime or a u prime or a z prime, whatever it is that's being primed. And we're like, we want to know the function that does that. So it's going to take a while to get there. And we won't always succeed, but that's okay. We're going to at least try. But there's something that we can do that's not so bad, which is we can verify a solution. So someone has come to us on a platter and they said, here's the answer. And we're like, is it? How do we know? Well, so the way that we know is we say, well, let's take your answer and we plug it in. And we check, does it hold? So there's like an example here. There's this differential equation. Y double prime minus 6y prime plus 9y equals 27x squared. And someone has come to us and said that this function for y equals x times e to the 3x plus 3x squared plus 4x plus 2 is indeed a solution. Well, we don't just have to take their word for it. We can find out. So the process is not so bad. The idea is plug it in. Now, what do we mean by plug it in? Well, it means we take this y and we plug it into each place that involves y. So there's 3 places that involve y. There's that y double prime, there's that y prime, and then there's the y. And we just plug it in and we check. So, how do we start? Well, the best way to start is to say, let's look at our pieces. So we have x e to the 3x plus 3x squared plus 4x plus 2. I'm just copying right now. Nothing too bad. What's the next thing we should do? Yeah, let's find y prime, because we're going to need it. All right, good practice. We need practice. What's the derivative of x times e to the 3x? All right, I'm hearing a 3x e to the 3x. Is that it? Plus, yeah, plus the 6x, right? Plus e to 3x. Okay, all right. I was getting excited, getting ahead of myself. All right, so don't forget, calculus rules still apply. So when I'm taking the derivative of x times e to 3x, what's the rule? Product rule. Product rule. Now, how do you know it's the product rule? Because it's a product. Yes, that's the secret. You know you're going to use the product rule because there's a product. Aha! It's like we named them good names. Okay, and so what happened here is you have to, everybody gets a turn in the product rule. So it's like, all right, in the first round, we'll have the derivative of just e to the 3x and leave x alone. So that's where this 3 came from. It's the derivative of e to the 3x. And of course, to take the derivative of e to the 3x, what rule did you use? Chain rule. See, all these rules are almost becoming second nature to you. But, they're still there. So that's the first part. It's x times the derivative of e to the 3x. The second part, derivative of x is 1 times e to the 3x. So derivative of the first times the second plus the second times the derivative of the first. Okay, we're not done. Derivative of 3x squared. 6x. Derivative of 4x. 4, good. Derivative of 2. 0. Our favorite answer. Hopefully we're going to learn that we really love 0. It's a wonderful, wonderful thing. All right, what's next? Yeah, second derivative, y double prime. We're on a roll. All right, what's the derivative of 3x e to the 3x? All right, 9x e to the 3x. So keeping that sort of 3x alone, times by the derivative of e to the 3x, there's another 3 that comes down. 3 times 3 is 9. What else do you have? So from here, we'd have 3e to the 3x, right? Because we'd have this, you have to take the derivative of the x term. Let's just sort of write e to the 3x here, because we're going to be sneaky. What's the root of e to the 3x? 3e to the 3x. So we're going to have a 3e to the 3x from here, a 3e to the 3x from there. Their powers combined give us 6. Yeah. All right, plus anything else? Plus 6. Okay. And the root of 4 is 0. All right. So now what do we want to do? Well, now we can plug it in. We say, what do we want? Well, we want to have one of these, because there's y double prime. We want to have, for y prime, we want to have minus 6 of those. And then for the y, we want to have 9 of those. So I'm taking my combination here. So on the left-hand side, well, we got one of the y double primes, minus 6s of the y primes, plus 9 of the y's. All right, no big surprises. Okay, so let's deal with the x e to 3x. So from the y double prime term, what do we have? How many do we have? We have 9 of them. From the y prime term, how many are we going to have? So there's x e to the 3x here. Negative 18, because that negative 6 is multiplying. Negative 6 times 3, negative 18. From the y term, what will we have? 9. All right, we'll clean that up in a second. Okay, let's deal with the e to the 3x terms. How many are we getting from the y double prime part? 6. There's 1 times 6. How many from the y prime part? Negative 6. Okay, now we'll come to the x squared part. How many x squareds are we getting? Well, none in y double prime, none in y prime. How many up here? 27. All right. How about for x? What do we have? Well, none for y double prime. How about here? Negative 36, right? Negative 6 times 6. Negative 36. How about from the y term? Positive 36. And since we're running out of space, we'll go up. Okay, constants. From the y double prime, we have 6 y prime. Negative 24. And then from the y, plus 18. Okay. Well, let's see if anything simplifies. 9 minus 18 plus 9? 0. 6 minus 6? 0. 27 is 27. Minus 36 plus 36? 0. 6 minus 24 plus 18? 0. So that it all collapses, and we're left with 27x squared. And then we say, aha, and we smile because life is good. We verified it. It works. This particular function solves that differential equation. Now, you might wonder, will we ever get to the point where we can start with that function and find that answer? And the answer is actually pretty soon, within the next couple of weeks. So, okay, so that's in one example of verify. We'll do one or two more here. But on a side note, this will be helpful as we get ready for the quiz. We can sometimes use the ideas of verifying to help find a solution. And you might say, well, how do you do that? Well, the way verifying works is you plug something in and you check. So you say, well, I have a guess. And your guess might involve some parameter, or it might be a specific function, it just depends. Say, all right, I have my guess, I plug it in. And then I check to see what happens. So I simplify, and it might be that it works, and like, oh, that was a great guess. Or it might be that it doesn't work, and that's okay. We say, okay, what needs to happen? Maybe I have to choose a parameter the right way, or maybe it's like, I see that I failed. but perhaps I can make a better guess. In fact, this is a lot of way that math and science gets done. You try something, and then you see what happens. It probably doesn't work. But you learn something from your mistake. You're like, aha, I can try something better next time. And after a few iterations, you got it. So that can work really well. Now the third step, still trying to figure that out. And the last step, of course, profit. All right, once we have that step 3, we're all going to be doing great. All right, so let's do a really simple example. And audience participation moment here, of course. We're going to find a solution to the form y equals e to the bx for the differential equation, but we haven't written it all down. This is your chance to get some input here. All right, so what would you like y double prime to be?
0.
You'd want it to be 0, but let's pick something more interesting. Someone said 14. Well, that's a very interesting thing, but okay, that's all right. How about that y prime? 6. Okay, we can work with that. How about that y? 10, 9? Well, we'll try it, and we'll see what happens. Maybe let's make this -9, just so things don't get too crazy. All right, so 14y double prime minus 6y prime minus 9y. Okay, so I didn't know ahead of time that these were the numbers. And, well, that's what I claim. You know, you're like, oh, did Steve plant the people in the audience? No. Totally random. Okay, so we're going to find a solution. But it tells us, here's the kind of solution we're looking for. E to the bx. So it's like, we have a solution in mind. So we say, all right, if y is e to the bx, what does y prime equal? Yeah, b e to the bx. The b comes down. What about y double prime? B squared e to the bx. And so we're going to plug these in. So we're going to have 14 and times y double prime, so that's b squared e to the bx, minus 6 times y prime, b e to the bx, and then minus 9 times y, which is e to the bx, equals 0. All right. Now, is this a solution? Well, if this is a solution, what needs to be true? Now, all this has to equal 0. That's a lot, Steve. Well, can we simplify anything on this left-hand side? Yeah, all these terms have e to the bx. Since that's common, pull it out. So e to the bx times 14 b squared minus 6b minus 9 equals 0. So now we have two things multiplying together to equal 0. This is a wonderful thing because there's a cool fact. If two things multiply together and the result is 0, what has to be true? One of them has to be 0. Now question, can the e to the bx, could this ever equal 0? No. Okay, you're out. Which means that this part has to equal 0. So we're like, oh. So really, as long as we can find some value for b, so that 14b squared minus 6b minus 9 equals 0, then that b will be the right choice for b, so that e to the bx is a solution. But how can we solve something like this? Yeah, quadratic formula. Good times. Should we recall what the quadratic formula is? If you have ax squared plus bx plus c equals 0, that's how you start. Then what you have is you say, hey, that says x equals, man, I feel bad choosing b as our answer, but all right, negative b plus or minus the square root b squared minus 4ac all over 2a. We'll use things like the quadratic formula a non-trivial amount of time this semester. Okay, so here we go. Once we figure out what the b's are, then we're home free. Okay, so here, that negative b means just the negative of what's there, so that's minus 6 is 6, plus minus the square root. The b squared would become 36 minus 4 times 14 times negative 9, all over 28. Okay, now 4 times 14 times negative 9 is a number. I've been told that by experts. And so here we go. Our two solutions are, because it says find a solution. It doesn't say find b, it says find a solution. So it's y equals e to the 6 plus the square root of 36 plus 4 times 14 times 9. That's a 6. All over 28 x. And y equals e to the 6 minus the square root of 36 plus 4 times 14 times 9, all over 28 times x. This is the danger, of course, when you ask for people to say, give me a number, any number. Wait, not that number. So, all right. I mean, we could probably figure this out. What? 4 times 14, that's 56. 56 times 9 would be 514. 504? That was close. Plus 36 is 540, which is a number. All right, that checks out. It is a number. I verified that. All right, so there you go. There you go. Now, before we leave, I just want to pause and say, one thing we should take away from this is that we really love e to the x. We love the function e to the x. It's our favorite function, and you're going to see it over and over and over again. So oftentimes when it comes to guessing, e to the x is involved. But why? What's so cool about e to the x?
When we differentiate it, it gives itself.
Yeah. When you differentiate e to the x, you have e to the x. And so we're like, wow, it's something which is really simple for derivatives. And we're working with equations that involve derivatives. So it's good to have a function that's very simple. So you're going to like e to the x. You're going to see it frequently as we go on this semester. Okay, another idea is what's called an initial value problem. And the idea of an initial value problem says, hey, we're going to have you solve a differential equation, but oftentimes when you solve a differential equation, there's a constant involved somewhere. There's a c floating around. You say, look, I want not just any solution. I don't want a family of solutions. I want my solution, the one that's just right. And so that means we have to solve for our constant that shows up. So let's go through and do an example. Now, I should note there's a little pro tip here. And number of constraints, or if you like, the number of constants, should almost always correspond to the number of derivatives. It's a really exceptional case when it doesn't. So if it's a first order differential equation, you should have one derivative, which means you have one constant. Second order differential equation, two derivatives, two constants, so forth and so on. Okay, so we'll do this one a little bit quicker. So verify natural log x plus c is a solution. Find the particular solution which satisfies y of 0 equals 1. All right. Well, so to verify, we need to check e to the y times y prime equals 1. Now, y is this natural log of x plus c. What is y prime? One over x plus c. Good. The differentiation of log is 1 over. So we have e to the natural log of x plus c times 1 over x plus c. But what's true about e and log? they're inverses of each other, and so they undo each other. So in essence, you can think of they're canceling. So it's x plus c times 1 over x plus c. So, but what is that? That's 1. Okay, so good. This is the verification. We're happy because both sides agree. All right, that's the first sentence. Now, find the particular solution which satisfies y of 0 equals 1. Now let's parse this really quickly. Y of 0 equals 1 says that you have a choice, x equals something, y equals something. What does x equal and y equal in this statement? 0, 1. So the way you should see this is like when you put in x equals 0, the output is, for y, number 1. So that says when you come to your function here, y equals natural log of x plus c, the way you use this is you say, all right, we're going to put in 0 for our x, and we're going to put in 1 for our y. So we get then that, for our choice for c, we need 1 equals the natural log of c. Well, which number, when you take the natural log of it, gives you 1? Some people are saying 0. Some people are saying 1. Some people are using the alphabet. The alphabet people win. It's E. Now, remember, natural log is oftentimes log base E. And if we think about the same process of before, where we said, oh, E and log undo each other, you can just take both sides, raise it. E to the 1 is E to the log C, and then E to the log C becomes C. And so we get that C equals E. So there we go. There we go. All right. Now, the next part, we're going to talk for a moment about an idea here. It's called mathematical modeling. And this is from the book. It's not hypercritical, but I think it's sort of a nice philosophy. And the idea here is we have some situation which we're trying to understand. Usually some real-world problem. So we're not trying to, buy cabbages from your local cabbage supplier. But no, we have something to describe. And the question is, well, how do we go about using math? And the way we do it is there's this sort of cycle here. It says, all right, we come up with some way to describe the situation. So that's our formulate. How can we describe something with a simple differential equation? So like Hooke's law. And then what we do is we do our analyze. Now, this, by the way, the analyze is oftentimes where we would say you solve the differential equation. So you say, okay, I've set up my formula. That was in the formula. I guess I should say what's happening here. And then we solve it. And then we say, okay, great. We interpret it. Now the interpretation says, is this any good? Maybe, maybe not. As someone came up to me after class on Monday and said, Hooke's law doesn't take into account friction. Oh, you're right. That says we need to improve it. And so we do another formulation. So it's this wonderful circle, always going around. But we're not going to spend too much time. More of this is a philosophy in the background. But we do want to get to the point where we say, at least we can understand the ideas behind formulating. We're not going to have to do too many setups, but we should say, all right, we understand the ideas and we can do it in some simple cases. So we'll do an example here. Set up a differential equation for the curve y equals f of x, which satisfies that the tangent line to the curve at a point x comma y hits the axis at the point 3x comma 0. Okay, so there's some curve we don't know. So there's this function that describes it. And we're told something about the tangent line. Now, a couple things jump out to us. One is it says, set up a differential equation. You might say, where's the derivative? Well, we'll get to that. And, but how do we start? How do we start? Well, what's something that could help us to understand what's going on? Okay, someone has said a graph. I like that idea. Pictures are good. I like pictures. Okay, so here we'll draw a rough picture. Doesn't have to be super precise. Here's the point x comma y. The point 3x comma 0, well, that says you go to whatever your x-coordinate is 3 times further out. 0 says you're on the x-axis. So there's 3x comma 0. And now, notice it says the tangent line at this point hits the axis. So we say, so that's cool. So there's our tangent line. So we now know what our tangent line to y equals f of x at the point x comma y. Well, what are some interesting things that you can say about a tangent line? Somebody said the derivative. What do you mean by the derivative?
Not sure, kind of a pot shot.
Not sure, kind of a pot shot. Okay, but I like that idea. Yes, tangent lines have something to do with derivatives.
The slope of the tangent line is the derivative of the function?
Ooh, the slope of the tangent line is the derivative of the function. Does that sound right? Because it is. It is right. So yeah, so there's a key idea here. So the derivative gives the slope of the tangent line. And we're like, oh, it's all coming together. It's like it was meant to be. So we say, hey, this is good. Because notice, what's this? It's a derivative. And we want derivatives because we want a differential equation. Better have a derivative somewhere. We say, that's good. So we say, okay, so y prime has to be the slope of our tangent line. Can we figure out the slope of the tangent line from this picture? Okay, how do you do it? Rise over run? Okay, so what's our rise over run? So, how much did we rise? Negative y, if we start there. How much did we run? 2x. So rise over run would be? Negative y over 2x. Okay, so what do we have? Well, if we read this sentence here, we said we're looking for a differential equation which satisfies that the tangent line to the curve at the point hits the axis at the point 3x 0. So we found our tangent line. We said, here's our tangent line. Here's our slope. Well, yeah, life is good. So what's the next step for this part of the problem?
Integrate that and add c to it?
Integrate. We're doing setup. We don't have to solve. Our next step is to box it. We set it up. We've got our answer. So that's good. Now, quick question here. What if instead we'd use the normal line? Well, wait, what's the normal line? Perpendicular. So when you hear the word normal, you think perpendicular. Okay, so we want normal. So we want it to be perpendicular. Right angle. Well, do we have to do a lot of work? Or can we just write down the answer?
Change the negative to a positive.
Negative to a positive? Okay, so quick callback to algebra. Good old days of algebra. If two lines intersect perpendicularly, how are their slopes related? Negative reciprocals. You remember? That's wonderful. Okay, we have our slope here. So what should we do to that slope? Negative reciprocal it. So what's the negative reciprocal of negative y over 2x? 2x over y. And that's the answer to the second part. And there we go. All right. Well, it's time for our next problem. So a rumor is spreading through a community with a fixed population P. The number of people who have heard the rumor so far is W. Wonderful letters. At any given time, the number of people that learn about the rumor is proportional to the square root of how many people have not yet heard the rumor. What's the differential equation that's hiding in this problem? So let's start, learning to parse these things. Now, oftentimes if you're reading a paragraph, you're like, I got to do a word problem. Your eye immediately gets drawn to anything that looks mathy. So it's like, I see this P and W is like mathy. And then it's like, that's it. Well, that's not a lot, but okay. At least we have those. Now, between those two, P and W, which one is the interesting one? In other words, like one of these is fixed and one of these is changing. Which one is fixed? P is fixed. So we're kind of probably going to be like, okay, the differential equation is going to have to be in terms of the W. W is our focus. All right. Now, there is a word that oftentimes masquerades. It really should be important words. When you see this word is, what does that really mean? Equals. So if you see a sentence with the word is, it's like, oh, I have something before the is. I have something after the is. Let's put them together. So let's start with what's before. The number of people that learn about the rumor. What is that? Well, it's not W, because W is the total number of people who know the rumor. The number of people who learn about it, those are like, oh, I've just learned about it. So somebody said the change. The change in W. When we say change in W, what do we use? W prime. So this part, this first part here, that's our W prime. Okay, so we have W prime. The is our equals. Proportional. Whenever you see something that says proportional, what do you throw in? So like Hooke's law, we said that it's proportional to how far you pull. There was a constant involved. So whenever there's a word proportional, that says, oh, there's just some constant that has to be figured out. So we throw in a K. So that's what proportional is. The square root, okay. Well, what should we put down? Yeah, a square root. Like, wow. It's like it was all there the whole time. Of how many people who have not yet heard the rumor? Okay, so how many people have not yet heard the rumor? P minus W. And there we go. That's our differential equation. How'd you do? All right. It gets easier. All right. Well, shifting gears, just a quick run through some terminology. We've already been using some of this terminology, so it's not going to be too surprising. We've talked about the order of a differential equation, and it's just the highest derivative involved. So you can look at a differential equation problem, and you can say, if I have something like y prime plus 9y to the 7th equals 11x, what's the order? It's a first order. But you may say, well, wait, y is raised to the 7th power. But it's not a derivative. It's something else. When we're talking about order, we're after the derivative. And on a side note, be comfortable with the notation. So if we say something like y9, but I use parentheses, what does that represent? 9th derivative. And you're like, well, why do we do that? Well, because it's easier than writing this and saying, okay, that's also the 9th derivative. But you're like, really? Or is it like y raised to the 111,111,111? No, it's the 9th derivative. So just make sure you know your notation. Now, they might do things that are sneaky on you and not write the highest order term first. We see through their tricks. They're not going to catch us. We're on to them. We're on to them. All right. Now, the next thing is this notion of what's called an ordinary differential equation, which is what we're going to focus on. So this is our class, an ODE. So that is just the ordinary kind of derivatives, the kind of derivatives that you'll see walking around campus at any given time. And so that just means what? Well, it means you have functions with one input. Y depends only on x, or maybe z depends only on t. The name of your variables can vary, but there's just a single thing that's going into your function. Now, there's another idea which is called partial differential equations. Those are nicknamed PDEs. So that's the other thing. And this is not our class. And so if you like partial differential equations, there are courses that do that. And they very interesting topics. And oftentimes, it's probably, in some sense, more relevant because it turns out that in the real world, it's not as simple as like one in, one out. Now, there's not just one input to one output, but there's many things which are varying. So you might have things like a function where you have it depending on x and t. So you might want to know fxx plus ftt equals 0. This is an example of a kind of partial. Now, if you're not familiar with this notation, these subscripts are meaning take derivatives with respect to x. This is just notation from that you'll see, for example, in multivariable calculus. So all our derivatives that we're going to focus on are just, there's one variable that's going into our function. The last thing, which we don't need to worry about, but we'll mention in passing, is we have normal form. And that just says, get the highest order derivative by itself. Y prime is a function of xy. And this is more just for some technical side notes. And we're not going to get really much into too many technical things. But we're going to just say a few words in the next couple of minutes that it's good to have this as a frame of reference. All right. So there's a big question that runs in the background. And we're trying to solve a differential equation, but you might ask the question, well, are you going to find a solution? And that's a non-trivial thing, because there are differential equations which are not solvable. There are no solutions. And then there's other weird things that can happen then when you say, oh, there are solutions. In fact, tons of them. And our goal is to say, well, you know, what we really want in an ideal scenario is the following, where if I have a differential equation, which is telling me how I change, and I have initial conditions, which is telling me how I start, that I should only have one possible curve associated with me. Because if I know where to start and I know how to change, I should only be doing one thing. And the answer is, it turns out that basically, yeah, that's going to be what happens most of the time. And so this is all background. We're not going to test you heavily on this, but it's good to understand that the mathematicians have dug into it, and they said the following. We've discovered this. It says, hey, if you have a differential equation, if your function here, so you've isolated your highest derivative, if your function is nice, so the first level of nice, it's continuous, then you have at least one solution. You may have several, but you have at least one. You're guaranteed a solution. If it's even nicer than that, which means if you took the derivative only with respect to y of the function, and that was also good, then not only do you have a solution, it's a unique solution. So if you have y prime equals something which is a nice expression, which is what you'll be dealing with in this class, you're guaranteed a unique solution. Now, solutions there's other limiting things that come into play. You'll see that there's some statements that this solution only holds near the point x equals a. All of calculus is based off of this idea. You know what's happening nearby. Calculus is all about the nearness. You know, the tangent line is a good approximation near the point of tangency. But you might say, what happens if I stray a little bit? Well, all bets are off. in some sense. And there are things which can happen. For example, your function might be good at one point, but you move, and all of a sudden it's no longer good. There's a discontinuity. Okay, so there's a limitation there. Another thing which can happen is you might get asymptotes, which aren't immediately obvious from the way your differential equation is set up. And you can't push past an asymptote. Now you might say, well, why not? I mean, the function's defined on the other side of the asymptote, so why can't you go past it? And the issue is the way differential equations work is you know where you currently are. The differential equation says how you should change. Well, you can't go through an asymptote because at the asymptote you're not ever on it. You get close to it, but you can't ever get on it. So you can't get past it. All right, so we're just going to run through. We'll probably do this a little bit quickly here. And just using these two facts. Does a solution exist? Is the solution unique? So remember, we think of y prime equals f of xy. If it's nice, it exists. If it's really nice, it's unique. So, for example, here, f of xy is 2x cubed plus y squared. Is that a nice function? In other words, is it continuous in terms of x and y? Got a 50-50 shot. Yeah, it is. Good. Is it a really nice function? So if you imagine taking the derivative of that with respect to y, do you get a nice thing out? Yeah. So this is great. We might be able to solve that. Or maybe not, I don't know. Who knows? How about this one? Y prime equals the square root of x minus y. Y of 3 equals minus 2. Is that nice? Well, it doesn't have to be nice everywhere. It has to be nice near our point. So what's our point? X equals 3, y equals minus 2. So think of this as 3 minus minus 2. That's basically the inside is around 5. Is square root of 5 nice? Or I should say, is square root nice around 5? Around 5, it's doing pretty good. So is there a solution? Yes. Is it unique? Can you take the derivative of a square root?
Yes.
And around 5, is it good to go?
Yes.
Yes. Okay, how about this one? Same function. But what's changed? Our points. 1, 1. What's our inside looking like? 0. Is this good? No. Square root of 0 is bad. No. If it doesn't exist, unique, forget about it, hopeless. All right. Y prime equals 4x, y times y prime equals 4x minus 4, y of 1 equals 0. All right. Are we guaranteed to exist? I hear a lot of yeses. So I'm going to go ahead and write no. What's wrong? What did I do to you that was sneaky? See, there's a y there. That y has to go over. So y prime is really 4x minus 4 divided by y, and I'm at a point where y is 0. Ah, that's right. Be ready to rewrite your equations. Yep, that's a true statement. True that, true that. Y prime equals the fifth root of y. Y of 2 equals 3. Are we good to go with the fifth root of a function? Yeah, it's pretty good. How about the derivatives? How's that looking? Yeah, life is good. How about the fifth root of y? Y of 1 equals 0. Well, is it continuous? Yes, because the fifth root looks something like this. You're fine. But what about a derivative? Yeah, the derivative is not nice, so you're not guaranteed it's unique. How about this one? Xy prime equals 3y, y of 0 equals 0. Because you're dividing by 0. So that you're not guaranteed that it exists. Now, I got a minute left. I'm just going to ask a question. We've just said that we are not guaranteed the solution exists. But I claim that there is a solution. Now you might say, whoa, what solution does that? It's this solution called y equals 0 is a solution. You can check. It satisfies both sides of the equation. So wait, does that contradict what we've said over here? And the answer is it doesn't contradict, because this just says, you know, it's not an if and only if. It just says if you're in a nice situation, we'll guarantee it. But if you're in a not nice situation, all bets are off, you don't know. In other words, more work, more work. All right. We'll stop here and we'll pick up again next time.